A telescope just revealed the impossible. Our universe, once thought to span 14 billion light-years, actually stretches 93 billion. This isn't just bigger, it's stranger than we ever imagined. The James Webb Telescope peered into what we believed was an empty patch of sky. What it found hiding in the darkness was utterly staggering: 800,000 galaxies. These weren't just any galaxies. They were ancient behemoths, already formed when the cosmos itself was a mere 300 million years old, far too early to be so developed by our previous understanding. And not just galaxies. Webb found black holes billions of times more massive than they should be, and vast structures stretching millions of light-years across. Everything we believed about the universe's size, its early formation, and the very timeline of cosmic evolution was, in essence, wrong. It was a cosmic reset. If you're ready to see what's truly out there, to confront a universe far grander and more puzzling than imagined, hit that like button and subscribe. We begin our journey into the rewritten history of the cosmos now. Brace yourself. To understand Webb's revolutionary insights, we must first grasp a fundamental principle: light takes time to travel. This isn't just about speed, it's about seeing the past. When you glance at an object a mile away, you're not seeing it as it is right now. You're perceiving it as it was a mere 5 microseconds ago. Look at our moon, and you're witnessing it 8 seconds in the past. Its light, though fast, carries echoes of what already happened. Gaze at the nearest star, and you're seeing light that embarked on its journey 4 years before today. This isn't speculation, it's confirmed science. Every single photon traversing the vastness of space acts as a tiny time capsule, meticulously carrying an image of the precise moment it began its epic journey. The James Webb Space Telescope, our most powerful eye on the cosmos, is positioned 1 million miles from Earth, perpetually staring into the profound darkness. Its colossal mirror, spanning 21 feet across, is meticulously coated in gold, specifically designed not to capture visible light, but infrared. Infrared light is the cosmic fossil that remains after visible light has been dramatically stretched by the continuous expansion of the universe itself. Think of it like the sound of an ambulance siren passing you on the highway. The pitch of the sound drops as the ambulance moves further away. Light behaves in a strikingly similar fashion across cosmic distances. As the universe expands, it stretches the wavelengths of light, shifting them towards the red end of the spectrum. So, Webb isn't merely observing objects far away in space, it's effectively looking backward through time itself, perceiving the universe in its infancy. The most distant galaxy it has yet found emitted its light a mind-boggling 13.5 billion years ago. That light has been traveling for almost the entire history of existence. This means we're observing this ancient galaxy as it looked when the universe was just 290 million years old, a mere cosmic toddler. To put that into stark perspective, if the universe's entire age were condensed into a single year, this galaxy would have formed on January 2nd. When that ancient light began its colossal journey, Earth didn't even exist. Our sun hadn't formed, and the Milky Way was still a nascent swirl of cosmic gas. Dinosaurs, humans, entire civilizations, everything we know came and went while those photons relentlessly crossed the void. Every image captured by Webb is, in essence, a fossil. A perfectly preserved moment, eternally frozen in light, offering a glimpse into a primordial past. Webb spent nearly 10 hours patiently gathering light to capture just one ancient galaxy. 10 hours of collecting photons that had traveled for 13.5 billion years. The sheer patience required for such an endeavor is truly staggering. But how do scientists confirm these unfathomable distances? Scientists employed an instrument called a spectrograph. This device splits light into its constituent colors, much like a prism beautifully creating a rainbow. Specific patterns within that cosmic rainbow reveal precisely how fast the universe has been expanding since that light was originally emitted. The further away an object is, the more its light has been stretched and shifted towards the red end of the spectrum, a phenomenon known as redshift. This record-breaking galaxy exhibited a redshift of 14.32, the highest ever confirmed for a distant galaxy. What does this profound measurement mean for us? We are not simply observing distant objects, we are directly witnessing the universe's childhood, peering into its earliest developmental stages. We're seeing the very first structures that would eventually give rise to everything we know, every star, every planet, every atom in your body. All can trace their cosmic lineage directly back to these primordial moments. However, this vast distance presents a profound problem. A problem scientists never fully anticipated. The galaxy, bearing a rather unpoetic serial number, JADES, GS Z14-0, was first spotted in late 2023. Scientists initially spent months doubting their own observations. It appeared far too bright, far too large, and far too developed for an object that shouldn't even exist yet. But when Webb spectrograph was finally aimed at this peculiar galaxy in January 2024, their deepest suspicions were confirmed. This cosmic anomaly truly sits 13.5 billion light-years away, having formed a mere 290 million years after the Big Bang itself. This places it squarely within an epoch known as cosmic dawn, a time when the very first stars were supposedly just beginning to flicker into existence. Emphasis on supposedly. Here's the core of the problem: this seemingly ordinary galaxy measures over 1,600 light-years across. While tiny compared to our modern galaxies, this size is enormous for its incredibly young age. It shouldn't have had time to grow so large. Even more perplexing, it contains several hundred million times the mass of our Sun, all tightly packed into surprisingly young stellar populations. The very light we detect originates from these newly born stars, blazing ferociously with intense ultraviolet radiation, confirmed by spectral analysis. Theoretical models consistently predicted that early galaxies would be small, dim, and simple collections of only a few million stars at most. The universe, at just 290 million years old, shouldn't have realistically had enough time to build anything remotely substantial. Gravity, the cosmic architect, works slowly. Gas gradually collapses, and stars form over millions of years. This process is inherently gradual. Even the invisible dark matter halos, essential for seeding galaxy formation, require immense time to accumulate sufficient material. Yet there it sits, JADES, GS Z14-0, bright enough that Webb could have easily detected it even if it were 10 times fainter. This singular detail sends shivers down the spines of astronomers, because it strongly suggests this impossibly bright galaxy isn't alone. If one such anomaly exists at this distance, then dozens, perhaps hundreds, more are likely hiding in regions Webb hasn't even surveyed yet. Indeed, the team found a second galaxy, nearly as distant, labeled JADES, GS Z14-1. Two record-breaking galaxies, in the very same field of view. Both exhibiting properties that directly contradict our standard cosmological models. Both producing starlight at rates that should be fundamentally impossible. What makes researchers especially uneasy is the specific chemical composition of these galaxies. Spectral lines revealed not just hydrogen and helium, but heavier elements. Elements like carbon, oxygen, and nitrogen. These atoms, crucial for life, only form deep inside stars, then spread through space when those stars explode. This implies an entire earlier generation of stars must have already lived and died before these galaxies even formed. The timeline keeps getting pushed backward. One astronomer vividly described finding this galaxy as akin to excavating a smartphone amongst ancient Roman ruins. The technology is simply too advanced for its era. Its structure is too sophisticated, its brightness too intense. It defies the very notion of early in cosmic terms. This discovery forced scientists to extend humanity's view into the cosmic past by a staggering 40% during Webb's first 18 months of operation. 40% deeper into time than we had ever seen before. But what does this mean for our understanding of the universe's true scale? The question nobody can fully answer is, if galaxies this massive existed this early, what else are we profoundly missing? Where does our current knowledge break down? Here's where the universe dramatically stops making intuitive sense. Light, as we know, travels at an astonishing 186,000 miles per second. Nothing, absolutely nothing, moves faster. This is a fundamental law of physics, confirmed by every single measurement we've ever made. In just 1 year, light covers approximately 6 trillion miles. Now, multiply that by the universe's estimated age of 13.8 billion years. The simple math suggests the observable universe should stretch 13.8 billion light-years in every direction. Except, that's completely wrong. The actual, confirmed edge of the observable universe sits a staggering 46.5 billion light-years away in every direction. Not 13.8, but 46.5. This means the total diameter of our cosmic bubble measures an astonishing 93 billion light-years across. We reside in a sphere of space. A sphere nearly 7 times wider than the maximum distance light could possibly have traveled in the universe's entire lifetime. This isn't a mistake, it's expansion. Space itself is stretching. Imagine drawing dots on a balloon, then inflating it. The dots move apart, even though they're not traveling across the balloon's surface. The surface between them is growing. Space works in precisely the same way. Galaxies aren't flying through space, space is actively carrying them apart. When that distant galaxy emitted its light 13.5 billion years ago, it was much, much closer to us than it is today. That galaxy has been continuously moving away from us for the entire time its light traveled toward us. It's a cosmic treadmill effect. By the time that ancient light finally reaches our telescopes, the galaxy that emitted it has drifted to a current distance of 46 billion light-years. You're running forward, but the treadmill pulls you backward. You might eventually reach them, but they'll be much farther away than when you started. Light does the exact same thing, perpetually fighting against the relentless tide of cosmic expansion. Here's what makes this whole situation profoundly strange: regions of the universe actually exist far beyond that 46.5 billion light-year limit. We know they're there because space itself extends infinitely in all directions. Our observable universe is simply the portion where light has had enough time to reach us. Beyond that boundary, countless galaxies shine, stars explode, and planets orbit. We just can't see them. And we never will. Even more unsettling, the expansion rate isn't constant, it's actively accelerating, a phenomenon confirmed by observations of distant supernovae. This acceleration is attributed to something called dark energy, a mysterious force that currently comprises a staggering 68% of everything that exists. Dark energy's density remains bizarrely constant as space expands, meaning its total amount increases as the universe grows larger. The universe is simultaneously finite in what we can observe, yet infinitely vast in what actually exists. And every second, the edge of what we can see grows larger. But space itself grows faster. Distant galaxies are perpetually disappearing beyond our causal reach, fading into an eternal cosmic night. And stranger still, the expansion rate seems to be subtly different depending on where exactly we look. This is the heart of the Hubble tension. Webb meticulously stared at a patch of sky slightly larger than 3 full moons for a staggering 250 hours. This region is aptly named the Cosmos Webb field. When the Hubble Space Telescope examined this very same area, it found roughly 10,000 galaxies. Scientists considered that a complete census. They were dramatically wrong, by a factor of 80. The final Webb image contains 797,942 galaxies. Nearly 800,000 distinct collections of stars. Each one potentially containing billions or even trillions of stellar masses. This single image required combining over 10,000 individual exposures. Carefully aligned and corrected for observational errors to produce this unprecedented cosmic tapestry. To truly grasp the scale, imagine printing the famous Hubble ultra-deep field on a standard sheet of paper. The Webb image would need to be printed 13 feet tall by 13 feet wide. A truly wall-sized mural of cosmic history, revealing intricate details at the same level of resolution. But this image is more than just pretty pictures. Every single galaxy captured within this image tells a unique story. Some formed 12 billion years ago, when the universe was young and chaotic. Others took shape relatively recently, just a few billion years back. The catalog itself includes measurements for each galaxy's distance and brightness, its mass, and its rate of star formation. Scientists can now meticulously track how galaxies evolved across 98% of cosmic time. What makes this image truly revolutionary isn't just the sheer number of galaxies, it's their distribution, their intricate cosmic dance. The galaxies aren't scattered randomly. They cluster along invisible threads, they gather at intersections, and they conspicuously avoid certain regions entirely. This striking pattern reveals the cosmic web, the largest known structure in the universe. A vast, intricate network of dark matter filaments. These filaments meticulously connect every major mass concentration in the entire universe. Every galaxy, every star, every planet. Webb's unparalleled infrared vision has pierced through thick cosmic dust that previously obscured entire populations of galaxies from older surveys. What once appeared as empty, dark regions in visible light now blazes with intense activity in infrared. Dusty nurseries where new stars are actively forming. Ancient galaxies whose light has been stretched to wavelengths human eyes simply can't detect. Objects Hubble literally couldn't see. The dedicated team behind this monumental achievement spent years developing the technology to precisely measure the properties of 800,000 galaxies simultaneously. Photometry to gauge brightness, morphology to classify shapes, redshift calculations to determine distances, and physical parameters to accurately estimate masses and ages. This monumental catalog represents one of the highest quality data sets ever compiled in the history of astronomy, freely released to the public. The images, the measurements, the entire catalog, along with an interactive viewer, allow anyone to search for specific objects or explore random patches of deep space. Before Webb launched, astronomers optimistically predicted they would find approximately 10 times fewer galaxies at these extreme distances. They estimated galaxies forming within the first 500 million years would be incredibly rare, perhaps a few dozen in a survey of this magnitude. The actual count exceeded predictions by a factor of 10, placing hundreds of extremely distant galaxies squarely into a cosmic era that should have been nearly empty. Something fundamental about early galaxy formation is demonstrably wrong in our current models. The universe is far more active than we believed. The Big Bang, the genesis of everything, occurred 13.8 billion years ago. This cornerstone of cosmology is confirmed by multiple independent measurements. Immediately afterward, the universe was incredibly smooth and nearly uniform. Tiny density fluctuations existed, but matter was spread almost evenly throughout space. Gravity, over immense spans of time, amplifies these subtle fluctuations, gradually pulling matter into clumps that eventually evolve into stars and galaxies. This process, by all accounts, should be slow, predictable, and gradual. Current models meticulously estimate how quickly the very first structures could have possibly formed. Gas needs sufficient time to cool for gravity to compress it. Dark matter halos need to accumulate enough mass to attract ordinary matter. And stars need to ignite, producing the heavier elements that, in turn, seed future star formation. Each step requires millions of years. The math behind this intricate cosmic choreography adds up to a clear prediction of how many galaxies should exist at any given cosmic age. Webb, however, found 10 times more galaxies in the early universe than those predictions allowed. 10 times. Researchers meticulously checked their instruments, verified their measurements, and rigorously examined the data for any potential errors. Everything consistently confirmed the same, seemingly impossible result. Within the first 500 million years after the Big Bang, the cosmos was teeming with galaxies. Bright ones, massive ones, galaxies containing billions of stellar masses worth of raw material. The universe was simply producing too much light, too early. It had only a paltry 400 million years to form structures containing 1 billion times the mass of our Sun. We simply don't know how to make that happen. Not with our current understanding of physics, not with our current understanding of how matter behaves. It's a fundamental challenge to our cosmic rulebook. One speculative explanation suggests that stars formed far more efficiently in the early universe. Perhaps gas collapsed faster due to a denser cosmos. Perhaps gravitational collapse worked differently when space was more compressed. Or perhaps environmental conditions allowed star formation to proceed at rates currently impossible. But this is purely speculation, not confirmed theory. The observations are real, undeniable. The explanations, however, remain deeply uncertain. Another intriguing possibility involves the mysterious dark matter. Different models of dark matter predict wildly different abundances of dark matter halos in the early universe. If dark matter behaved subtly differently than the standard model assumes, it could have created conditions that significantly accelerated galaxy formation. Webb's precise measurements might ultimately help us distinguish between these competing dark matter theories, guiding us towards a more accurate understanding. What truly troubles astronomers most is not a single anomalous galaxy, but the sheer consistency of the surprise. It's not one, it's hundreds. Across multiple surveys, in different regions of the sky, utilizing different instruments, Webb consistently reveals the same pattern. Far more galaxies exist than current theories suggest should be possible. The implications of this reach far beyond simple number counts. If galaxies formed this abundantly and this early, they must have profoundly influenced their surroundings sooner than our models currently expect. They would have begun reionizing the universe earlier, enriching space with vital heavy elements at a much faster rate. They would have seeded the formation of larger structures at an earlier epoch. This implies a complete revision of the entire timeline of cosmic evolution. Every textbook chapter on the early universe might now be considered incomplete. And some of those early galaxies are so massive, they border on the truly impossible. Astronomers discovered universe breakers, galaxies in the infant universe that weighed 100 times more than theory permits. These objects appeared so impossibly immense that researchers initially called them universe breakers because their very existence seemed to violate the fundamental laws of cosmology. The core of the problem ultimately comes down to time. Building a truly massive galaxy requires an intricate sequence of events. Dark matter must first collapse into a halo, then ordinary matter falls into that halo, then gas cools and fragments, then stars form. Then those stars must live out their lives and die, then the heavy elements they produce seed the next generation of stars. This entire cycle must repeat over and over again as the galaxy gradually grows. Each individual step has a minimum duration, rigidly determined by physics. You cannot compress gas faster than the speed of sound without creating shock waves that would simply heat it back up. You cannot form stars instantly. You cannot skip the necessary waiting period while stellar evolution dutifully proceeds. The standard model of cosmology calculates exactly how massive a galaxy can become at any given age. Yet some early galaxies observed by Webb dramatically exceeded those theoretical limits by factors of 10 to 100. They appeared to contain more stars than should be remotely possible given the limited time available. Their sheer brightness suggested stellar populations too large for that cosmic era. Scientists scrambled to explain this glaring discrepancy. Perhaps the galaxies weren't quite as massive as they appeared. Perhaps bright, active galactic nuclei, powered by central black holes, made them seem much bigger and brighter than they truly were. Perhaps supermassive black holes at their centers contributed significant light, making the galaxy seem more luminous than the stars alone could produce. Recent analysis suggests this explanation is partially correct, though not entirely. Some of these universe breakers do indeed harbor extremely bright black holes. These black holes inflated their apparent mass. When astronomers meticulously account for black hole contributions and reanalyze the data, the galaxies indeed shrink. They shrink to more reasonable sizes. They're still massive for their age, but they no longer break the universe. However, even after these corrections, a problem remains. Roughly twice as many massive galaxies still exist in the early universe as models predict. The discrepancy has narrowed from a factor of 100 to a factor of 2. But the fundamental problem hasn't disappeared. Something about early galaxy formation remains stubbornly unexplained, a persistent cosmic puzzle. One team directly compared Webb's groundbreaking observations to Hubble's previous census of galaxies at similar distances. Hubble had been observing for decades, meticulously building a representative sample of what existed in various cosmic epochs. If the standard model were correct, Webb and Hubble should logically see similar distributions of galaxy masses. Any increase in Webb's count should come from detecting fainter galaxies. Instead, Webb found far more bright, massive galaxies than Hubble's data suggested should even exist. This inconsistency is a direct challenge. This inconsistency points to either unique environmental differences in the early universe or critical gaps in our understanding of how efficiently matter converts into stars. What remains absolutely certain is that massive structures appeared far earlier than expected, forcing a re-evaluation of cosmic timelines. And at the very centers of some of these early galaxies, lurking in the primordial darkness, are monsters even more perplexing. A supermassive black hole resides at the heart of galaxy GN-Z11, one of the most distant galaxies ever observed. This black hole existed when the universe was only 430 million years old. Its mass equals millions, or possibly billions, of times the mass of our Sun. That should be fundamentally impossible. Black holes typically form when massive stars collapse. A star needs to be at least 20 times more massive than our own to create a black hole when it dies. The resulting black hole usually weighs 10 to 100 times what our Sun weighs. From there, it can grow by consuming gas, dust, and other stars. But this accretion process, by its very nature, takes time. Billions of years. 430 million years simply isn't enough time. Even if a black hole formed immediately after the Big Bang and continuously consumed material at the maximum possible rate, it couldn't grow. It couldn't grow to billions of stellar masses by this early date. The very physics of matter falling into black holes imposes strict limits on growth speed. Yet there it was. Webb detected extremely dense gas surrounding this black hole, a clear signature of rapid accretion. The black hole was actively feeding, pulling matter inward at tremendous rates. Spectral analysis revealed patterns that uniquely appear near supermassive black holes consuming gas. This galaxy isn't unique. Webb has since discovered multiple supermassive black holes existing surprisingly early in the universe. Some even appear more massive than theoretically expected for their cosmic age. Each new discovery only deepens the mystery. How did these colossal objects grow so incredibly large, so astonishingly quickly? Scientists have proposed several theories to try and explain this. One intriguing possibility involves dark stars. These are theoretical objects, not powered by nuclear fusion, but by dark matter annihilation. Such stars could grow to millions of times the mass of our Sun before collapsing directly into massive black holes, providing a significant head start on growth. Another theory suggests that in the dense, early universe, gas clouds could have directly collapsed into massive black holes, bypassing the star formation stage entirely. If conditions were just right, a cloud containing 100,000 stellar masses might have compressed directly into an equivalent black hole. This has never been observed. However, mathematical models strongly suggest it's theoretically possible. A third explanation involves rapid collisions. If smaller black holes frequently merged in the crowded early universe, they could have rapidly built up mass faster than simple accretion alone allows. Gravitational wave detectors have definitively confirmed that black hole mergers occur. Perhaps they simply happened far more often in the ancient past. What makes these early, massive black holes especially important is their profound role in galaxy evolution. They aren't passive cosmic bystanders. They actively blast out enormous amounts of energy as matter spirals inward. This powerful radiation heats surrounding gas. And this heating can either trigger star formation or, paradoxically, shut it down completely. Supermassive black holes fundamentally help regulate how galaxies grow. Finding them so early in cosmic history means they exerted a powerful influence on cosmic evolution from nearly the very beginning. Their pervasive presence could help explain some of the unexpected galaxy properties Webb continues to uncover, bridging perplexing gaps in our understanding. But before these black holes even existed, something even stranger might have burned brightly in the primordial darkness. Something theoretical. Scientists detected something truly peculiar in the spectrum of galaxy GS 3073. The light contained an extreme imbalance of nitrogen compared to oxygen. The ratio measured an incredibly high 0.46, which is utterly bizarre for any normal stellar population. Ordinary stars don't naturally produce that chemical signature. And stellar explosions don't create it either. But theoretical models precisely predicted this exact signature from a highly unusual type of star, never before observed. Primordial monster stars, thousands of times more massive than our Sun. These theoretical giants would have formed in the very early universe. They would have formed from clouds of pure hydrogen and helium. No heavy elements existed yet to contaminate the gas. The first generation of stars, known as population 3 stars, consisted entirely of the lightest atoms. Without heavy elements to help cool the gas, these clouds collapsed into much more massive stars. A single monster star might have weighed 1,000 to 10,000 times what our Sun weighs. It would have burned incredibly hot. Its core would have fused helium into carbon at ferocious rates. This carbon would then capture additional helium nuclei through a process called the carbon-nitrogen-oxygen cycle. This cycle would have produced vast, detectable quantities of nitrogen. These stars would burn brilliantly for only a few million years, before exhausting their fuel. When they died, they wouldn't explode like normal supernovae. Instead, they would collapse directly into massive black holes. But during their brief, brilliant lives, they would spew nitrogen-rich material into space through powerful stellar winds, detectable across the cosmos. That very material is what Webb meticulously detected in GS 3073. The unmistakable chemical fingerprint of monster stars that lived and died billions of years ago. The nitrogen they produced remained in the galaxy, mixed with later generations of normal stars, creating the unusual spectrum astronomers observed. This discovery provides the first clear, observational evidence that population 3 monster stars actually existed. For decades, they remained purely theoretical. Mathematical models showed they should form, but nobody had ever detected their unique chemical signatures in real galaxies. Webb changed that reality. The implications of this discovery reach far beyond merely confirming a prediction. Monster stars help solve the supermassive black hole problem. If stars this massive collapsed into black holes weighing thousands or tens of thousands of stellar masses, those black holes would have a huge head start on growth. They could reach supermassive status much faster than black holes formed from normal stars, resolving a major cosmic headache. Monster stars also made a significant contribution to reionization, the period when the first sources of light began ionizing the hydrogen gas that filled space. Their intense ultraviolet radiation would have stripped electrons from atoms across vast regions, making the universe transparent to light. This crucial process transformed the cosmos from an opaque fog into the clear medium we observe today, allowing light to travel freely. Additionally, these colossal stars produced the very first heavy elements. Every atom of carbon, oxygen, and nitrogen in the early universe came from stellar interiors. Monster stars forged these elements faster and in greater quantities than normal stars could. They seeded the formation of subsequent star generations that could then form planets and, eventually, life itself. The universe's largest stars burned at the beginning. Not now. They were brief, but ultimately essential architects of everything that followed. Yet even these cosmic giants were just individual objects. The universe's true scale truly reveals itself in its grandest, most elaborate structures, far beyond single stars or even galaxies. The universe isn't uniformly distributed. Galaxies cluster along vast threads of dark matter that stretch for tens of millions to hundreds of millions of light-years across space. These intricate filaments connect at massive intersections where thousands of galaxies accumulate. And between these threads lie vast, empty regions called voids. Vast, empty regions where almost nothing exists. This stunning, interconnected pattern is called the cosmic web. It's consistently confirmed as the largest structure in the entire universe. Every major concentration of matter, every galaxy, connects to it. The web pervades the entire observable cosmos, meticulously integrating all gravitationally bound structures into one colossal, interconnected network. The web initially formed from tiny density fluctuations in the earliest moments of the universe. Regions that were slightly denser than average. Had slightly more gravity. They pulled in more matter, which, in turn, increased their gravitational pull even further. This cosmic feedback loop amplified over billions of years, creating denser and denser regions connected by streams of infalling material. Think of it like water flowing downhill into valleys. The valleys represent regions of higher dark matter density. The streams represent filaments, where matter flows from one concentration to another. Over immense cosmic time, these streams become cosmic highways of galaxies, traveling along invisible gravitational corridors. Dark matter, a mysterious substance, provides the very scaffolding for this cosmic architecture. It comprises 85% of all matter in the universe, a figure confirmed by its undeniable gravitational effects on visible matter. Dark matter doesn't emit or absorb light, nor does it interact with electromagnetic radiation. We detect it solely through its gravity. Wherever dark matter concentrates, ordinary, visible matter dutifully follows, drawn in by its unseen gravitational pull. Scientists meticulously map the cosmic web by surveying millions of galaxies and precisely measuring their positions in three-dimensional space. Distinct patterns emerge. Galaxies align along specific directions, they cluster at nodes where multiple filaments intersect, and they avoid regions between filaments. This intricate distribution directly reveals the underlying dark matter structure. Even our own cosmic neighborhood, the local group, which includes our Milky Way galaxy and Andromeda, sits on a visible filament connecting the Fornax cluster to the Virgo cluster. This particular filament stretches approximately 110 million light-years across. Light from some parts of our local structure departed when dinosaurs still roamed the Earth. The largest concentrations of galaxies occur where multiple filaments precisely meet. These intersections become galaxy clusters, the most massive gravitationally bound objects in all of existence. A typical cluster might contain 100 to 1,000 galaxies, with a total mass exceeding 100,000 trillion stellar masses. They represent the extremely high-density nodes of the cosmic web. Material perpetually flows along these intricate filaments, steadily drawn towards these colossal clusters. Galaxies that initially started isolated gradually drift along the threads, eventually joining these dense cluster populations. As they travel, they frequently interact with other galaxies. Colossal collisions occur, galaxies merge, and gas gets violently stripped away by the hot plasma filling the space between galaxies. These environmental effects fundamentally transform star-forming spiral galaxies into redder, quiescent elliptical ones. The cluster environment shapes galaxy evolution. Recent, groundbreaking observations have finally detected dark matter directly on these cosmic filaments for the very first time. This was achieved using gravitational lensing. Scientists observed how light from distant background objects precisely bent around the invisible mass concentrations along the cosmic web threads. These meticulous measurements definitively confirmed that dark matter truly does line these filaments, not just concentrate at nodes. For the very first time, scientists detected dark matter hanging from the cosmic web's terminal segments, the thin, delicate threads connecting clusters to individual galaxies. This remarkable confirmation of theoretical predictions fundamentally reshapes our understanding of how the largest structure in the universe organizes space. But Webb, in its relentless pursuit of cosmic truth, revealed something even more extreme. Something that challenges the very limits of what the Webb can build. Astronomers, utilizing Webb data, discovered a massive chain of at least 20 closely packed galaxies, stretching across the cosmos. They aptly named it the cosmic vine. It gracefully swoops through space in a distinctive bow shape, spanning over 12 million light-years long and approximately 650,000 light-years wide. For comparison, our entire Milky Way galaxy measures only 100,000 light-years across. All 20 galaxies exhibited a redshift, meaning their light traveled between 11 and 12 billion years to reach us. They existed when the universe was only a few billion years old. The vine formed during an era when such colossal structures shouldn't have had time to assemble. What makes the cosmic vine truly remarkable is its immense size compared to other galaxy groups discovered at similar distances. It's significantly larger than anything else ever found at this cosmic epoch. The structure appears to be in the process of becoming a galaxy cluster, one of the universe's most massive formations. Current mass estimates place the vine at approximately 260 billion stellar masses. That's already enormous, but it's still growing. Galaxies continue to drift along the filament, drawn by the combined gravity of the structure. Eventually, over the next several billion years, these galaxies will merge. They will merge into a unified, colossal cluster. What truly puzzles researchers is the peculiar state of the two largest galaxies within the vine. When scientists analyzed the wavelengths of light these galaxies emitted, they found that star formation had almost completely stopped. The galaxies are classified as quiescent, meaning they're no longer actively producing new stars. This is highly unusual for the early universe, where most galaxies are still vigorously forming stars. Finding large galaxies that have already used up their gas reserve strongly suggests something dramatic occurred. One possibility is that these galaxies resulted from recent mergers. When galaxies collide, they can trigger massive bursts of star formation that rapidly consume all available gas within a relatively short period. The intense collision would heat the gas to extreme temperatures. Hot gas doesn't collapse easily to form stars, or it can be expelled from the galaxy entirely by the sheer energy released during the merger. This would leave behind a galaxy full of existing stars but utterly depleted of the raw material needed to build new ones. Another compelling explanation involves the environment. Galaxies residing in dense cosmic structures experience fundamentally different conditions than isolated galaxies. They constantly pass through hot plasma, filling the space between galaxies. This plasma can violently strip away their gas through a process called ram pressure stripping. Imagine sticking your hand out of a car window at highway speeds. The air resistance pushes your hand backward. Gas in galaxies experiences similar forces. When the galaxy moves through the hot medium between galaxies. The cosmic vine represents just one striking example of unexpected large-scale structure in the early universe. Webb keeps finding massive concentrations that formed far faster than our current models predict. Each new discovery adds more evidence that something about early structure formation proceeded more efficiently than standard theory allows. These enormous structures don't exist in isolation. They are part of a much larger population of galaxy groups that Webb has catalogued across cosmic time. A dedicated team of astronomers meticulously compiled the largest and deepest sample of galaxy groups ever observed. They detected 1,678 galaxy groups and protoclusters, spanning from 12 billion years ago to approximately 1 billion years ago. This catalog maps cosmic family trees from near the very beginning. Each galaxy group represents a collection of galaxies held together by gravity. They are smaller than massive clusters, but larger than individual galaxies. Think of them as neighborhoods in the cosmic web, distinct communities connected by the larger structure, but maintaining their own local gravitational identity. What makes this Webb catalog truly revolutionary is its unprecedented depth. Previous surveys could only glimpse fragmented parts of this evolutionary sequence. They might catch groups at one cosmic epoch or another, but they could never truly trace continuous development across billions of years. Webb fundamentally changed that limitation. Its incredible infrared sensitivity allows for the detection of galaxies 1 billion times fainter than what human eyes can perceive, unveiling unseen cosmic evolution. The catalog vividly reveals how galaxy groups evolve over immense cosmic timescales. In the early universe, groups appear chaotic. Galaxies exhibit irregular shapes, star formation proceeds vigorously, and the overall structures are loose, not yet settled into stable configurations. As cosmic time progresses, these groups become increasingly organized. Galaxies develop more symmetrical shapes, like elegant spirals and ellipses. Star formation gradually slows down, a process known as quenching. The groups themselves grow more compact as gravity pulls members closer together. Eventually, many groups merge into larger, more massive clusters. This evolution directly reflects broader processes shaping cosmic structure. Dark matter halos steadily accumulate over time, and smaller halos merge into larger ones. Gas heats up as it falls into these expanding halos. Supermassive black holes at galactic centers blast energy into the surrounding space. All these dynamic effects combine to transform the properties of galaxies and the groups they inhabit. Scientists can now meticulously track individual galaxy populations through multiple evolutionary stages. They identify galaxies at one distance, then meticulously look for similar galaxies at other distances to see how that specific population changed over cosmic time. This creates a compelling narrative of cosmic history, vividly showing how different types of galaxies emerged and evolved from their primordial beginnings. The catalog also reveals crucial environmental effects. Galaxies in dense groups behave profoundly differently than isolated field galaxies. Group members experience more frequent interactions, they collide more often. Their gas gets violently heated by the hot plasma filling the space between them. These powerful environmental factors accelerate evolution, transforming active, star-forming galaxies into quiescent ones much faster than would happen in isolation. One particularly striking finding involves the dramatic transition from chaotic to organized. The shift occurs fairly rapidly in cosmic terms, over just a few billion years. Early groups exhibit high star formation rates and irregular morphologies. Later groups show low star formation and remarkably regular shapes. This swift transformation precisely coincides with the era when dark matter accumulation shifted from rapid, chaotic growth to slower, more consolidated gathering. This comprehensive catalog provides strong observational evidence for theories about how structure fundamentally forms in the universe. It confirms predictions about halo assembly, and it validates models of environmental quenching. It beautifully demonstrates how the cosmic web organizes matter on the very largest scales. Yet even with nearly 1,700 groups meticulously catalogued, vast regions of space contain absolutely nothing at all. Between the intricate filaments of the cosmic web, enormous, empty regions, called voids, stretch across the universe. These cosmic vacuums contain almost no galaxies, almost no stars, and almost no matter of any kind. They can extend for hundreds of millions of light-years in every direction, representing the largest continuous volumes of emptiness in the universe. Imagine standing precisely in the middle of a void. Look in any direction, and you would see profound darkness, extending for tens of millions of light-years. Before encountering the nearest galaxy, the void would appear as a vast, cosmic desert, a seemingly empty realm where structure formation simply failed to occur. Voids form through a process that is the exact opposite of how clusters form. Regions that initially started slightly less dense than average had slightly less gravity. Matter gradually flowed out of these regions towards denser areas, further decreasing their already low density. This cosmic drainage process continued for billions of years, creating progressively vaster, emptier regions. The cosmic web itself perpetually evolves by expanding these cosmic voids and simultaneously compressing the filaments. It's a dynamic interplay of growth and contraction. The largest known void stretches approximately 1 billion light-years across. That's roughly 1% of the observable universe's diameter. If you started at one end and traveled at the speed of light, you would spend 1 billion years traversing nothing but empty space before reaching the other side. Scientists actively study voids because they provide pristine laboratories for understanding cosmic expansion and dark energy. In dense regions, local gravitational effects complicate measurements. Galaxies move under the combined influence of cosmic expansion and local attraction. In voids, local effects are minimal. Galaxies move almost exclusively under the influence of cosmic expansion, making them ideal tracers of how fast the universe is expanding. Void statistics also rigorously test cosmological models. The number, size, and distribution of voids depend sensitively on dark matter properties and initial conditions after the Big Bang. So far, void counts consistently match predictions, providing compelling evidence that current models capture the broad outlines of structure formation correctly. What makes voids, in some ways, slightly unsettling is their sheer extremity. The universe could have distributed matter far more evenly. Instead, it chose to create these vast, empty regions and concentrate almost everything into thin, intricate threads and dense, massive nodes. This stark contrast vividly emphasizes how gravity fundamentally organizes space, pulling matter together while simultaneously leaving enormous gaps. Within those colossal gaps, any civilization that arose would undoubtedly perceive a very different night sky than we do. They would observe far fewer galaxies. Their entire view of the cosmos would be dramatically limited, potentially leading to drastically different cosmic conclusions. Meanwhile, the light itself, traveling through both voids and filaments, undergoes a profound transformation that reveals just how far it has come. Every single wavelength of light, from the most distant galaxies, gets inexorably stretched by the relentless expansion of space. Ultraviolet light gracefully becomes visible light. Visible light, in turn, transforms into infrared. And infrared stretches even further into the beyond. This continuous stretching is known as redshift. The term arises from the fact that stretching wavelengths shifts light towards the red end of the spectrum. Blue light shifts to red, red shifts to infrared. The further a galaxy sits from us, the more its light has been stretched during its long cosmic transit. And the higher its redshift value. This value reveals precisely how much the universe has expanded since that light first began its journey. Scientists accurately measure redshift using spectroscopy, analyzing unique absorption and emission lines in the light spectrum. Specific atoms naturally emit light at precise, characteristic wavelengths. Hydrogen, for instance, produces a distinct line at 92 nanometers in the ultraviolet. When astronomers observe this exact line, but find it shifted all the way to 1380 nanometers in the infrared, they know. They know the light has been stretched by an astonishing factor of 15. This specific factor of 15 directly tells us how much the universe has expanded since the light was emitted. When a galaxy with a redshift of 14 emitted its light, the universe was 15 times smaller than it is today. All distances were 15 times shorter, all wavelengths were 15 times compressed. Space itself has grown 15-fold since those photons began their journey. Here's where this fundamental concept becomes truly visually dramatic. The early galaxy emitted predominantly ultraviolet and blue light from its hot, young stars. Yet we see none of that in its original form. Every single ultraviolet photon has dramatically shifted into near-infrared wavelengths, between 1 and 3 microns. And every visible photon has stretched into mid-infrared, between 3 and 10 microns. The entire original spectrum has fundamentally slid beyond what human eyes can detect. This is precisely why Webb was meticulously designed with infrared detectors. The telescope was specifically engineered to observe light from the most distant galaxies, knowing that light would inevitably arrive in infrared wavelengths. Previous telescopes, like Hubble, primarily operated in visible and ultraviolet light. They could detect some infrared, but not at the extreme sensitivity needed to observe these incredibly faint, high-redshift galaxies. Webb's instruments cover a vast range of infrared wavelengths, from 0.6 microns all the way to 28 microns. The telescope operates at temperatures near absolute zero. to prevent its own heat from overwhelming the faint infrared signals it's trying to detect. The result is truly revolutionary. Regions Hubble imaged as black voids now reveal intricate structure. Galaxies appear where absolutely nothing seemed to exist before. The cosmic landscape has gained depth and detail that was literally invisible just a few years ago. Cosmic dust itself plays a critical role in this revelation. Dust particles scatter and absorb visible light, effectively obscuring distant objects. However, dust allows infrared light to pass through relatively unimpeded. Star-forming regions, the very birthplaces of stars, are often shrouded in thick, opaque dust clouds. Hubble typically saw these regions as dark, empty patches. Webb, with its keen infrared vision, effortlessly sees through the dust, revealing the bustling stellar nurseries hidden inside. This effect appears throughout the universe. Dusty galaxies that appeared incredibly faint or were completely invisible in Hubble images now shine brightly in Webb observations. Scientists can now meticulously study star formation in environments that were previously completely opaque. They can accurately measure how much dust exists in different galaxies and at different cosmic epochs. They can determine how dust fundamentally affects galaxy evolution. The comparison between Hubble and Webb images is truly striking. Hubble typically shows a relatively sparse collection of bright, well-defined galaxies against a black background. Webb reveals those same bright galaxies, plus hundreds of thousands of fainter ones, filling the spaces between them. The universe appears far more crowded, far more active, and far more complex than ever before. This doesn't, however, mean that Hubble was somehow inferior. Hubble, in its illustrious career, fundamentally revolutionized our understanding of the cosmos. It discovered dark matter, it measured the universe's expansion rate, it determined the ages of the oldest stars, and it revealed supermassive black holes at galactic centers. Its contributions are immeasurable. But Hubble looked at the universe primarily through visible light eyes. It saw what humans would see if we could somehow travel to deep space and simply look around. Webb, on the other hand, sees infrared. A spectrum entirely invisible to human vision but absolutely critical for understanding the cosmos in its entirety. Together, Hubble and Webb provide complementary views. Views that, when combined, reveal far more than either could achieve alone. What Webb reveals in infrared shows that our visible light view of the universe is profoundly incomplete. Vast populations of objects exist that human eyes could never detect, no matter how powerful our vision became. The universe contains far more than our biology allows us to perceive. And what Webb sees strongly suggests the early universe was far more active than anyone ever expected. The Standard Model of Cosmology makes clear predictions about the early universe. After the Big Bang, space expanded and cooled. About 380,000 years later, atoms formed. Another few 100 million years passed before the first stars ignited. Those stars gradually gathered into the first galaxies. The process, by all accounts, should have been gradual, proceeding over hundreds of millions of years. Galaxies should have been rare in the first 500 million years, small, dim, simple structures containing relatively few stars. The universe simply hadn't had enough time to build anything elaborate. Webb's observations dramatically contradict this timeline. Within the first 400 million years, the cosmos was already producing enormous amounts of light. Bright, fully formed galaxies blazed across space. Massive structures had already assembled, defying the expected gradual pace of cosmic evolution. The early universe appears far more luminous than models predicted. Scientists are calling this the too much light, too early problem. The observations are clear, multiple independent surveys consistently confirm it. Different instruments verify it. The early universe was brighter than it should have been, given the available time for galaxy formation. One comprehensive measurement perfectly encapsulates this profound problem. Researchers calculated the total amount of light produced by all galaxies in the first billion years after the Big Bang. They compared this to theoretical predictions of how much light should exist, based on standard structure formation models. The observations dramatically exceeded predictions by factors ranging from 2 to 10, depending on the exact cosmic epoch examined. 2 to 10 times more light. That's not a subtle discrepancy, it's a fundamental challenge to our very understanding of how galaxies form and evolve. Something about the early universe allowed it to produce stars and galaxies far more efficiently than the same processes work today. Several explanations for this perplexing phenomenon have been proposed. Perhaps the initial mass function of stars was different in the early universe. The initial mass function describes the distribution of stellar masses when stars first form. Modern star formation typically produces mostly small stars, with a handful of massive ones. Maybe early star formation produced proportionally more massive stars. Massive stars burn brighter and hotter than small ones. So this shift in stellar populations could significantly increase the total light output of early galaxies. Another possibility involves star formation efficiency. In the modern universe, only a small fraction of available gas actually converts into stars. Most of the gas either gets heated, blown away, or simply remains in diffuse clouds. Perhaps in the early universe, environmental conditions allowed gas to convert into stars far more efficiently. Higher efficiency means more stars per unit of gas, thus producing significantly more light from the same initial amount of raw material. Black holes themselves might also contribute to this problem. Active galactic nuclei, powered by supermassive black holes consuming matter, can shine brighter than entire galaxies combined. If black holes were more common or more active in the early universe, they could account for some of the observed excess light. Recent observations from Webb strongly support this idea, showing that many early galaxies harbor extremely bright active nuclei. What makes this problem especially frustrating for theorists is that the observations keep pushing the timeline for early galaxy formation even earlier. First, Webb found surprisingly bright galaxies at 600 million years. Then at 500 million years. Then at 400 million years. Then at 300 million years. Each new, deeper discovery consistently reveals that the universe was already producing significant light even earlier than previously observed. The standard cosmological model isn't completely broken, it accurately predicts many other observables, like the cosmic microwave background, and the distribution of elements and large-scale structure. But it clearly misses something profoundly important about early galaxy formation. Resolving this persistent problem might require genuinely new physics. Perhaps dark matter behaves differently than assumed. Perhaps star formation proceeds through completely new, undiscovered mechanisms. Or perhaps the initial conditions after the Big Bang were more complex than current models capture. What remains undeniably certain is that the universe's infancy was far more active and brighter than anyone predicted. And the very light we see from that era, precisely because it has traveled across such immense distances, reveals just how truly limited our view is. Light originating from the absolute edge of the observable universe has been faithfully traveling for 13.8 billion years. During that immense span of time, cosmic expansion has carried the source of that light to a current distance of 46.5 billion light-years away. This defines the cosmic horizon, the limit of our observational reach. Everything within 46.5 billion light-years is observable in principle. Everything beyond that boundary, however, remains forever invisible to us. But space itself doesn't just stop at this observable edge. The universe demonstrably extends far beyond our horizon. Galaxies exist out there, stars shine, planets orbit, black holes consume matter. All of it proceeds completely unobservable from Earth. We know this because the observable universe appears roughly the same in all directions. It shows no sign of an edge or boundary. Galaxy distributions look strikingly similar, whether we examine regions to our north, south, east, or west. The cosmic microwave background, the afterglow of the Big Bang, has nearly identical properties across the entire sky. This remarkable uniformity suggests space continues. Space continues far beyond what we can currently see. Think about what this profound implication means. Our observable sphere is merely one bubble in an expanse that extends, perhaps, indefinitely. Our sphere has a radius of 46.5 billion light-years. Somewhere 47 billion light-years away, galaxies exist that we will simply never see. Their light hasn't had enough time to reach us yet. And even if given enough time, cosmic expansion actively prevents this. Space is expanding faster than those distant regions can send light toward us. Imagine someone running on a treadmill towards you while the treadmill continuously speeds up. If the treadmill accelerates faster than they can run, they'll never reach you. Despite running in your direction. Light from distant galaxies faces the exact same problem. Dark energy ensures that regions currently beyond the cosmic horizon are receding faster than light can travel through expanding space. Their light will never, ever reach us. The gap widens instead of narrowing. Those regions are causally disconnected from us. No signal, no particle, no information can ever traverse the expanding space to separate us. This creates truly strange implications. Events happening right now in those distant regions will simply never affect us. If a hypothetical civilization exists 50 billion light-years away, we will never be able to communicate with them. Their radio signals will never reach us. Our signals will never reach them. We effectively exist in separate, isolated pockets of space. As time passes, the situation worsens. Cosmic expansion is accelerating. Regions currently within our observable universe will eventually cross the horizon and disappear. Galaxies we can see today will redshift until their light becomes completely undetectable. Then they will fade from view entirely. Scientists calculate that in approximately 150 billion years, every galaxy outside our local gravitationally bound group will have disappeared. Beyond the cosmic horizon. Future observers in our galaxy will see a universe containing only the Milky Way, Andromeda, and a few dozen smaller galaxies. They might logically conclude that these few galaxies represent the entirety of the universe, unaware of the billions of galaxies that once filled the sky. We are truly fortunate to live in an era when the universe graciously reveals itself. We can see 13.8 billion years of cosmic history. We can observe the early universe, track galaxy evolution, and precisely measure cosmic expansion. Future civilizations might not have this profound opportunity. The accelerating expansion will inexorably erase the evidence. But even now, with all our advanced telescopes and technology, we see only a tiny fraction of what actually exists. The vast majority of the universe lies permanently beyond our reach. The observable universe, our cosmic bubble, measures 93 billion light-years across. That number seems truly enormous. It contains somewhere between hundreds of billions and trillions of galaxies. Countless stars. An unimaginable number of planets. Yet this entire sphere represents only what we can observe, not the totality of what exists. The actual universe is demonstrably larger, potentially much, much larger. Possibly even infinite. Current measurements strongly suggest space is geometrically flat. This implies that parallel lines remain parallel forever. Triangles drawn across cosmic distances have angles that sum precisely to 180 degrees. Euclidean geometry applies. And in flat, infinite space, the universe extends without bounds in all directions. If the universe is indeed infinite, then beyond our observable sphere, lies an infinite amount of space, containing an infinite number of galaxies, stretching on forever. For every single galaxy we can see, infinite galaxies exist that we cannot. For every star in the observable universe, infinite stars shine beyond our horizon. The numbers become literally meaningless, because infinity exceeds any finite count by an infinite amount. Some cosmological models suggest the universe is finite, but unbounded. Similar to the surface of a sphere. You could continuously travel in a straight line, eventually returning to your starting point. after circumnavigating the entire cosmic expanse. In such a universe, the total volume is vast, but ultimately finite. Estimates for finite universes often place the total diameter at hundreds of billions, or even trillions of light-years. Still vastly larger than what we can currently observe. Whether finite or infinite, the universe beyond our horizon contains structures and phenomena we cannot detect. Galaxy clusters form there, cosmic web filaments connect across distances we will never measure. Stars explode, black holes merge. Entire populations of objects exist in complete isolation from our observable region. This raises a profound question about scientific knowledge. We develop theories based on observations within our observable universe. We test those theories through rigorous experiment and measurement. Our most successful theories, like general relativity and quantum mechanics, have been verified countless times within the observable universe. But do they apply beyond our horizon? We assume physical laws are universal, but we cannot directly verify this assumption for regions we can never observe. Most scientists believe the universe is indeed uniform on the largest scales. The cosmological principle states that the universe looks roughly the same everywhere, when averaged over sufficiently large volumes. Our observable region appears typical, not special. If this principle holds, then regions beyond our horizon should contain similar densities of galaxies, similar structures, and similar physical processes. But we cannot definitively prove this. It's an assumption based on symmetry and simplicity, not direct observation. Perhaps regions beyond our horizon differ dramatically. Perhaps different physical constants apply. Perhaps entirely different forms of matter and energy dominate. The multiverse hypothesis takes this idea even further. Some inflationary cosmology models suggest our observable universe is just one bubble in a vast foam of separate universes. Each bubble underwent its own Big Bang-like event. Each evolved independently. Different physical laws might apply in different bubbles. We exist in this particular bubble because its properties happen to allow life to develop. Other bubbles might be sterile, lacking the right conditions for complexity to emerge. These profound ideas remain speculative. No observations currently confirm or rule out multiverse scenarios. They exist at the very boundary between physics and philosophy, addressing questions that might be fundamentally unanswerable through experiment. What we know with certainty, however, is that our observable universe does not represent all that exists. Space demonstrably extends beyond what we can see. Whether that extension is finite or infinite, uniform or varying, singular or multiple, remains unknown. And every location in that extended space has its own unique view of the cosmos. Stand anywhere in the universe and look around. You see a sphere of galaxies, extending to your cosmic horizon. Light from those galaxies has had sufficient time to reach you since the Big Bang. Beyond that horizon, galaxies exist that you cannot observe, because their light hasn't yet arrived. Now, imagine standing somewhere else, perhaps in a galaxy 46 billion light-years from Earth. From that distant location, you would see a completely different observable sphere. Galaxies visible from Earth would lie beyond their horizon. Conversely, galaxies invisible to us would be clearly observable from there. Every single location in space defines its own observable universe. The boundary of that observable region depends entirely on where you stand. What's inside one observer's horizon might be outside another's. No single perspective captures the totality of what exists. This creates strange and fascinating situations. Consider two galaxies separated by 90 billion light-years. Neither can observe the other. They exist in causally disconnected regions of space. Yet both might be observable from Earth if they happen to lie in opposite directions from us. We could see both, simultaneously, even though they cannot see each other. Or, consider a galaxy existing precisely at our cosmic horizon. Light from this galaxy is just now reaching us after traveling for 13.8 billion years. But from that galaxy's perspective, Earth lies at their cosmic horizon. Our light is just now reaching them. We see them in their distant past. They see us in our distant past. Neither observes the other as they currently are. This inherent asymmetry of observation reveals something fundamental about the universe's structure. Space has no single center, no truly privileged location. Every point can rightfully consider itself the center of its own observable sphere. The cosmic horizon surrounds every observer equally in all directions. If other civilizations exist in distant galaxies, they look at the universe and see patterns strikingly similar to what we observe. Galaxy distributions, cosmic web structure, the cosmic microwave background. But the specific galaxies they catalog would be completely different from ours. Their most distant galaxies would be utterly unknown to us. This intriguing fact raises interesting questions about communication. Suppose we detect a faint signal from a civilization 20 billion light-years away. We could theoretically communicate with them despite the enormous distance. We send a message. 20 billion years later, it arrives. They meticulously respond. 20 billion years after that, we receive their reply. The entire exchange would take 40 billion years. But it's theoretically possible. However, if a civilization exists 50 billion light-years away, communication becomes fundamentally impossible. They lie permanently beyond our cosmic horizon. Our signals simply cannot reach them. Their radio signals will never reach us. We are permanently isolated from each other. This fundamental limitation applies to all information. Any event occurring beyond the cosmic horizon cannot affect us causally. No particle, no photon, no gravitational wave can traverse the expanding space to deliver information about those distant events. They might as well exist in a completely separate universe for all the influence they have on our region. Yet from their perspective, they face identical limitations. They cannot observe us. They cannot communicate with us. They cannot be affected by events in our region. We exist in mutually exclusive observable universes. The full universe likely contains countless such observable spheres, each centered on different locations. Each revealing different subsets of the total cosmic population. And each observer would be equally justified in asking what their observations mean for their place in existence. Webb revealed a universe far larger, far more complex, and far more magnificent than we ever imagined. Not just larger in total extent, though that too, but larger in population. Trillions of galaxies instead of hundreds of billions. Each containing billions or trillions of stars. Each of those stars potentially hosting planets. The numbers escalate beyond comprehension. The Milky Way, our galactic home, seemed vast when we thought it was one among 200 billion galaxies. Now it might be one among 10 trillion or more. Earth shrinks in significance with every new discovery. We orbit an average star in an average galaxy in an average region of space. Nothing about our location appears special. We're not at any center. We're not in any unusual structure. We're thoroughly average in every measurable way. This humbling realization has been building for centuries. Copernicus showed that Earth orbits the Sun, not the other way around. Later astronomers showed our star is ordinary, one among hundreds of billions. Then we learned the Milky Way is just one galaxy among many. Now we learn that many means trillions. Each new discovery displaces humanity further from any sense of cosmic importance. We are not the center of the solar system, not the center of the galaxy, not even in a special galaxy. We're thoroughly average in every measurable way. Yet this apparent displacement brings with it a powerful new perspective. If trillions of galaxies exist, each with billions of stars and countless planets, the probability of other life existing somewhere becomes astronomically high. We are, in all likelihood, not alone. The cosmos is simply too vast, with too many opportunities for chemistry and evolution to unfold, for Earth to be unique. We are one outcome among potentially billions or trillions of instances where matter organized into living systems. Our particular history, our specific biology, our individual civilization might be unique. But life in general, intelligence in general, probably appears throughout the universe. We can never know for certain, however. Most of those potential civilizations lie permanently beyond the cosmic horizon. We cannot communicate with them. We cannot observe them. They cannot observe us. We exist in isolated pockets of space, despite being part of a potentially populous cosmos. For the civilizations that happen to reside within our observable sphere, detection remains incredibly difficult. Space is vast. Distances are enormous. Signals attenuate to undetectable levels across thousands or millions of light-years. The universe could be teeming with civilizations. All trying to communicate, all failing to bridge the vast gulfs between stars. Webb starkly reminds us of these cosmic gulfs. Every deep field image shows thousands of galaxies, each separated by millions or billions of light-years. Each containing billions of potential homes for life. Yet the distances render them inherently unreachable. We can see them. We can study them. We cannot visit them or communicate with anyone who might live there. What we can do is appreciate the sheer scale. Understand our precise place within it. Recognize that we are part of something unimaginably larger than ourselves. The universe is 93 billion light-years across in what we can see. Beyond that, it extends further, possibly infinitely. We occupy one planet, circling one star in one galaxy among trillions. That's not insignificant. That's our home. Our origin. Our context. Webb has starkly revealed just how large that context truly is. The universe is bigger, more complex, and more magnificent than we ever imagined. And we are privileged to live in an era when we can look out and see it, understand it, and marvel at our tiny, but precious place within it. At the very centers of some galaxies, a single light source burns with such incredible intensity, it actually outshines every other star in that entire galaxy combined. These enigmatic objects are called quasars. They represent the brightest, continuously shining objects in the universe, true cosmic beacons. A single quasar can emit more light than 1 trillion stars like our Sun. This astonishing energy output is staggering. More luminous than the combined light of hundreds of billions of stars, all compressed into a region smaller than our entire solar system. Quasars are powered by supermassive black holes. As gas spirals inward towards the black hole, friction heats it to millions of degrees. This superheated material violently radiates across the entire electromagnetic spectrum. The energy output is truly staggering. More luminous than the combined light of hundreds of billions of stars, all concentrated into a region smaller than our solar system. Webb has successfully detected quasars existing when the universe was less than 700 million years old, pushing the boundaries of cosmic discovery. These ancient quasars pose the exact same problem as early supermassive black holes: they shouldn't exist yet. Building a black hole massive enough to power a quasar should take billions of years. Yet there they are, blazing brightly in the infant cosmos. One particular quasar detected by Webb appears so incredibly bright that scientists initially questioned the accuracy of their own measurements. The object shines with the luminosity of 600 trillion stellar masses. 600 trillion. That's more energy than our entire Milky Way galaxy produces. Concentrated into a region perhaps a few light-months across. The light from this quasar has been faithfully traveling for over 13 billion years. During that entire immense journey, the quasar's radiation has been streaming through space in all directions. Only an infinitesimal fraction happened to travel in Earth's direction. The total energy this object has released into the cosmos is almost incomprehensible. Quasars also serve as invaluable cosmic flashlights. Their intense light illuminates gas clouds residing between them and Earth. When scientists analyze quasar spectra, they observe specific absorption lines. where intervening gas has absorbed specific wavelengths. These absorption features reveal the composition and temperature of intergalactic gas across billions of light-years. This powerful technique has successfully mapped the cosmic web in 3 dimensions, revealing its intricate structure and distribution. Gas along the filaments shows up as absorption in quasar light. Voids show minimal absorption. Dense regions show strong absorption. By observing many quasars in different directions, astronomers reconstruct the large-scale structure of the universe. Quasars, however, are not permanent. They represent a specific phase in galaxy evolution when the central black hole actively feeds on surrounding gas. Once the available gas is consumed or expelled, the quasar dramatically shuts down. The galaxy itself continues existing, but the brilliant central engine goes dark. The black hole remains dormant, patiently waiting for new material to fall inward. Our own Milky Way galaxy, it turns out, once hosted a powerful quasar. Evidence strongly suggests the Milky Way's central black hole consumed gas vigorously billions of years ago. The quasar phase ended when the fuel was depleted. Now the black hole sits relatively quiet, occasionally flaring when a stray star wanders too close or a gas cloud falls inward. Webb's unparalleled ability to detect these incredibly distant quasars helps constrain how quickly supermassive black holes grew in the early universe. Each new quasar discovery at high redshift pushes back the timeline for when these cosmic monsters became active. The data consistently suggests black hole growth happened faster than standard models allow, further contributing to the persistent mystery of early structure formation. What makes quasars especially valuable? For studying the universe's true scale, is their astonishing visibility across truly enormous distances. A quasar billions of light-years away can still be detected, precisely because it shines so brilliantly. Galaxies at similar distances, lacking a central quasar, might be too faint to see. But quasars loudly announce themselves. This means quasars often define the very frontier of observable space, serving as crucial markers. Webb has also captured breathtaking images of galaxies in the tumultuous process of merging. 2 massive collections of stars, gas, and dark matter, rushing toward each other at speeds measured in millions of miles per hour. When they finally meet, the ensuing collision fundamentally transforms both galaxies. Despite the inherent violence of the merger, individual stars rarely collide directly. The space inside galaxies is mostly empty. Stars are separated by vast distances. When 2 galaxies merge, their stars mostly pass through each other, like 2 swarms of gnats interpenetrating. The gas, however, behaves quite differently. Gas clouds from the 2 merging galaxies do collide. They crash together at tremendous velocities, creating shockwaves that compress the gas to extreme densities. This sudden compression triggers massive bursts of star formation. Thousands or even millions of new stars ignite within just a few million years. The merger region blazes with the brilliant light of newborn stellar populations. Webb observed one of the most striking examples of this cosmic violence ever photographed. 2 galaxies, designated ARP 107, are locked in a dramatic collision. The larger spiral galaxy is being violently disrupted by a smaller, elliptical intruder. The impact has already created brilliant knots of star formation, visible as bright blue regions in ultraviolet light, appearing red in Webb's infrared view due to redshift. The immense tidal forces during a merger are profound. Gravity pulls stars and gas into long, elegant streamers, extending hundreds of thousands of light-years from the main galactic bodies. These ethereal tidal tails eventually fall back into the merger remnant, but they create striking visual features during the collision process itself. Simulations consistently show that major mergers between similarly sized galaxies typically produce elliptical galaxies. The ordered structure of spiral arms gets violently destroyed. Stars end up on random, elliptical orbits around the newly merged galactic center. Gas often falls towards the core, where it either forms new stars or feeds the central black hole, creating an active galactic nucleus. The Milky Way, our very own galaxy, is currently headed towards an inevitable merger with its largest neighbor, Andromeda. The two galaxies are steadily approaching each other at approximately 250,000 miles per hour. In approximately 4 billion years, they will finally collide. The merger will take several billion years to complete. As the galaxies make multiple passes, gradually spiraling together due to powerful gravitational interactions and energy loss. When the Milky Way and Andromeda eventually merge, Earth's night sky will be dramatically transformed. Andromeda will grow larger in apparent size as it approaches, eventually filling a significant portion of the sky. During the merger itself, newly formed stars will blaze across the heavens, illuminating the cosmic dance. The combined galaxy, sometimes whimsically called Milkomeda, will be a colossal elliptical containing all the stars from both progenitors. Webb has also detected direct evidence of these galactic mergers occurring surprisingly early in the universe. Galaxies colliding when the cosmos was less than 1 billion years old. These early mergers might provide a crucial explanation for some of the unexpectedly massive galaxies found at high redshifts. Instead of growing gradually through steady star formation, galaxies could rapidly build mass by violently merging with their cosmic neighbors. The merger rate was demonstrably higher in the past. The universe was simply smaller and denser, meaning galaxies were closer together. And collisions happened far more frequently. As cosmic expansion continues, galaxies steadily separate. The merger rate naturally declines. In the distant future, galaxy mergers will become increasingly rare as dark energy pushes galaxy groups further and further apart. Every major elliptical galaxy we observe today almost certainly resulted from at least one major merger in its distant past. The smooth, featureless appearance of ellipticals belies their violent origin. The chaos of collision effectively erased any ordered structure, leaving behind a gravitationally relaxed system where stars orbit on random paths. Mergers also profoundly affect star formation in unexpected ways. Sometimes they trigger massive bursts of star formation, igniting new stellar nurseries. But sometimes, they mysteriously shut down star formation entirely. Webb captured one of the most spectacular examples of gravitational lensing ever photographed, a perfect ring of light. A shimmering Einstein ring, surrounding a massive foreground galaxy. This fascinating phenomenon was predicted by Einstein's theory of general relativity. Decades before anyone observed one. Gravity, according to Einstein, isn't just a force, it bends space itself. Massive objects create curves in the very fabric of spacetime. When light travels past a massive object, it follows these curves. From our perspective, the light's path appears bent. This captivating effect is known as gravitational lensing. Because massive objects effectively act like lenses, focusing and distorting light from background sources. When the alignment is perfect, extraordinary things happen. If a distant background galaxy, a massive foreground galaxy, and Earth happen to precisely line up, the background galaxy's light gets bent. It gets bent into a perfect ring shape around the foreground object. Every photon from the background galaxy that passes on one side of the foreground mass gets deflected toward us. The same effect happens on the other side. The result is light arriving from all directions around the lensing galaxy. The Einstein ring isn't actually circular, it's a sphere. We perceive it as a circle because we're looking at a three-dimensional effect projected onto our two-dimensional field of view. If you could move above or below the alignment, you would observe the ring at an angle, appearing elliptical. Einstein rings are incredibly rare, true cosmic jewels. They demand nearly perfect alignment between three distinct objects, separated by billions of light-years. Most lensing events, by contrast, create arcs or multiple images, instead of complete rings. But when a full ring does form, it provides powerful scientific opportunities, allowing for unprecedented cosmic measurements. Scientists use Einstein rings to precisely measure the mass of the foreground lensing galaxy. The degree of light bending directly depends on how much mass causes the deflection. By analyzing the ring's radius and the known distance to the background galaxy, astronomers can calculate the total mass of the foreground object, including dark matter. These meticulous measurements consistently reveal that dark matter extends far beyond the visible boundaries of galaxies. The Einstein ring size directly indicates how far the dark matter halo stretches into space. Typical results show dark matter distributed in a roughly spherical halo surrounding the luminous galaxy, with its mass concentrated toward the center and gradually declining outward. One specific Einstein ring, captured by Webb, showcases a galaxy that existed 13 billion years ago, dramatically lensed by a foreground galaxy only 4 billion light-years away. The background galaxy appears significantly magnified and brightened by the lensing effect. Instead of appearing as a faint smudge, too dim for detailed study, it shines as a bright ring, where scientists can meticulously analyze its spectral features and precisely measure star formation rates. This cosmic magnification effect effectively turns massive galaxy clusters into natural telescopes. They powerfully boost the light from extremely distant, background objects, making those distant galaxies far easier to study. Without lensing, many high-redshift galaxies would be too faint for Webb to observe in detail. Lensing, however, brings them into view, transforming their study from impossible to feasible. Galaxy clusters, those colossal cosmic cities, create even more dramatic lensing. The combined mass of hundreds or even thousands of galaxies, plus hot plasma, plus dark matter, creates incredibly strong gravitational fields. Background galaxies get dramatically stretched into long arcs. Some even appear multiple times as light takes different paths around the cluster. The resulting images look utterly bizarre, with galaxies warped into cosmic crescents and elongated streaks. Webb used this powerful effect deliberately. Scientists specifically pointed the telescope at known, massive clusters, understanding that these clusters would naturally magnify faint background galaxies. This brilliant strategy revealed some of the faintest and most distant galaxies ever detected. Objects that would be completely invisible without lensing became observable through the cluster's natural magnification. The most extreme lensing can magnify background objects by factors of 10 to 100. This fundamentally turns the study of very distant galaxies from impossible to feasible. And what scientists see when galaxies enter dense environments reveals dramatic transformations. When a galaxy falls into a massive cluster, it doesn't just gently settle into a stable orbit. It plunges violently through the cluster, at speeds reaching millions of miles per hour. During this tumultuous passage, the galaxy encounters a hostile environment that gradually tears away its vital gas. The space between galaxies in a cluster isn't empty. It's filled with extremely hot plasma, heated to tens of millions of degrees. This intergalactic medium is thin by Earth standards, but substantial on cosmic scales. When a galaxy moves through it at high velocity, the galaxy experiences a resistance similar to a car driving through water. This resistance is known as ram pressure. Ram pressure effectively strips gas from the galaxy. Observations show long tails of gas streaming behind galaxies as they plunge through clusters. These luminous tails can extend for hundreds of thousands of light-years, containing enough material to build millions or even billions of stars. Instead, the gas gets left behind in the cluster environment. Without gas, the galaxy simply cannot form new stars. Star formation, the very engine of galactic growth, stops within a few 100 million years. The galaxy transforms from a blue, star-forming spiral into a red, quiescent elliptical or lenticular galaxy. This process is called environmental quenching. Webb detected numerous examples of this quenching process. Galaxies in clusters consistently show much lower star formation rates than similar galaxies in less dense environments. The difference is truly dramatic. A galaxy in isolation might form several stellar masses worth of new stars per year. The same galaxy, after falling into a cluster, might form zero. The effect is especially pronounced for smaller galaxies. Massive galaxies have deeper gravitational wells that hold on to their gas more effectively. Smaller galaxies, however, have weaker gravity. Ram pressure can strip away their entire gas content in a single passage through the cluster core. They effectively become red and dead, containing only old stellar populations with no ongoing star formation. One image from Webb shows a striking example of this, a galaxy nicknamed the Jellyfish Galaxy, as it plunges through its host cluster. Ram pressure has stripped long, ethereal tentacles of gas and stars, trailing behind the main galactic body. Star formation continues within these gaseous tentacles for a brief period before the gas completely dissipates. The galaxy leaves behind a luminous trail. A radiant trail of star clusters, marking its path through the cluster. Tidal interactions, the gravitational ballet of merging galaxies, also play a significant role. The combined gravity of the cluster and neighboring galaxies actively pulls on the infalling galaxy. These immense tidal forces can strip away outer stars, leaving behind a smaller, more compact remnant. Over billions of years, large spiral galaxies that fall into clusters can be reduced to small elliptical galaxies. The cluster environment also prevents galaxies from reaccreting new gas from intergalactic space. In isolation, galaxies continuously draw in fresh material from surrounding cosmic web filaments. This replenishes gas consumed by ongoing star formation. In clusters, however, the hot intergalactic medium is too energetic. That hot gas is too energetic to be captured by individual galaxies. The supply of fresh gas gets effectively cut off. Scientists estimate that approximately half of all galaxies in the universe reside in clusters or groups. This means environmental effects profoundly influence the evolution of a huge fraction of the galactic population. Understanding how environment shapes galaxies is crucial for comprehending galaxies as a whole. And across cosmic time, these environmental effects have subtly changed the chemical composition of everything that exists. The early universe contained almost nothing but hydrogen and helium. These are the two lightest elements, forged in the very first minutes after the Big Bang. Everything else, every heavier element, came later. Forged inside stars and scattered throughout space when those stars finally died. Webb detected this chemical evolution by analyzing the spectra of galaxies at different distances. Nearby galaxies show spectral lines from many elements: carbon, oxygen, nitrogen, iron, silicon, magnesium. The full periodic table appears in their light. But the most distant galaxies primarily show hydrogen and helium, with only faint traces of heavier elements. This pattern reveals how the universe has been enriching itself with heavier elements over billions of years. The technical term for this chemical makeup is metallicity. Astronomers, perhaps somewhat confusingly, call anything heavier than helium a metal, even though elements like oxygen and carbon aren't metals in the chemistry sense. Low metallicity means few heavy elements. High metallicity means abundant heavy elements. The first stars formed from pure hydrogen and helium. When these massive stars exploded as supernovae, they ejected newly created heavy elements into the surrounding space. The next generation of stars formed from gas already enriched with these elements. When those stars died, they added even more heavy elements. Each successive stellar generation steadily increased the metallicity of the available gas, leading to a richer cosmic soup. Scientists measure this by meticulously examining absorption and emission lines in galaxy spectra. Specific elements produce characteristic patterns. Oxygen creates lines at particular wavelengths, carbon creates different lines. By measuring the strength of these lines relative to hydrogen, astronomers accurately determine how much of each element exists in the gas. Results show that metallicity consistently increases. It increases steadily from high redshift to low redshift. Galaxies at redshift 8 show metallicities around 2% of what we observe in nearby galaxies. Galaxies at redshift 4 show 20%. Galaxies at redshift 2 show 50%. By redshift 0, meaning the present day, metallicity reaches its current levels. This ongoing enrichment is absolutely crucial for planet formation and, ultimately, for life itself. Planets specifically require heavy elements. You cannot build a rocky world, capable of hosting life, from pure hydrogen and helium alone. Carbon-based life needs carbon, nitrogen, oxygen, phosphorus, and other elements. Early generations of stars diligently provided the raw materials for everything more complex than hydrogen gas. Our own Sun is a third-generation star, at minimum. It formed from gas already enriched by previous stellar generations. That gas contained the silicon, iron, oxygen, and other elements needed to build Earth and everything on it. Every single atom in your body, except for hydrogen, was created inside a star, and then released through a supernova or powerful stellar wind. Webb's observations dramatically show this enrichment proceeding faster in some environments than others. Dense regions where stars form rapidly accumulate heavy elements quickly. Sparse regions where star formation proceeds slowly remain metal poor for longer. Galaxy mergers accelerate enrichment by triggering intense starbursts that produce and disperse heavy elements rapidly. The most metal-poor galaxies Webb detected existed at high redshifts. These pristine systems contain gas that has experienced minimal stellar processing. Studying them reveals what the universe's raw material looked like before significant enrichment occurred. The composition precisely matches predictions. From Big Bang nucleosynthesis, the process that created elements in the very first minutes after the Big Bang. Interestingly, even in metal-poor galaxies, some elements appear more abundant than others. Oxygen, for instance, enriches faster than iron, because different types of stars produce different elements. Massive stars that die young produce mostly oxygen. Smaller stars that live longer produce more iron. The ratio of oxygen to iron reveals the history of star formation in a galaxy. By meticulously tracing metallicity across cosmic time, scientists precisely reconstruct the chemical evolution of the universe. From pure hydrogen to a cosmos where heavy elements comprise a few percent of all matter. That few percent made all the difference. That crucial percentage made planets, chemistry, and eventually life, possible. This realization is incredibly humbling.